Yes,
Okay,
red
perfect.
point.
Okay, so hi everyone. My name is Francisco Ponce. We'll start presenting my doctoral thesis, which title is Supporting Triage of Microservice Security Smell Using Trade-off Analysis. Before of everything, I want to thank everyone to be here. So I hope you enjoyed this brief description of all the work that we have done during these years. So let's start with a bit of context. In this case, my research is focused on microservice-based applications that are essentially service-oriented applications adhering to an extent set of design principles. Here we can find, for example, isolation of failures, decentralizations, horizontal scalability, and so on. This type of application enable building cloud-native applications that can fully exploit the capabilities of cloud computing, exhibiting distributed, dynamic, and fault-resilient behavior. So, a lot of companies started some years ago delivering their business through this type of application. So securing microservices is crucial in this context because a lot of business rely in this type of application in the current years. So it's sorry, in the current time. So we started by facing some challenge here in the context of microservice security. This challenge has been described in some literature. You have, in this case, all the reference in the footer of the PPT, but there is more literature. We can start by speaking about the how this type of application expose more endpoints because they are much more distributed than traditional, obviously monolithic application and other service-oriented applications. So microservice-based applications expose more endpoints, thus this enlarges considerably the surface prone to security attacks. In this context, it's also crucial to establish trust among the microservice forming an application to manage the distributed secrets that need to be shared between these microservices. Also, one of the challenges that we can find here is that the interaction between microservices should be secure, not only when they interact with external clients, but also between the microservices that form, in this case, a microservice applications. With regards to the research objectives of this thesis, we were interested in knowing what are the effects of bad security decisions for microservice-based applications. We also tried to do a bit of progress in how to detect and resolve security smells that are currently affecting microservice-based applications. We also were interested in know what are the impacts of microservice security smells on quality attributes besides security, because security is not a quality attribute that doesn't interact with the rest. Here we are all have the knowledge, right? The quality attribute interact with others, that there is trade-off and so on. So we were interested in knowing about these specific impacts. And finally, we were interested in knowing how to determine which microservices security smells resolve first. With regards of the contributions, just a brief summary of this. For the field objectives of what are the effects of bad security decisions for microservice-based application, we generated a taxonomy of microservice security smells and refactoring. We also generated a taxonomy of microservice security, bad and good practices. We then moved to in order to find a way, right, to detect and resolve the security smells that could affect a microservice application. We generated a model-driven end-to-end approach for the resolution of the security smells that affect an application. Then, with regards of the what are the impacts of microservice security on quality attributes besides security, we presented or we proposed in general visual and holistic panoramas of the positive and negative impact of these security smells. We also identified and validated 35 impacts of the microservice security smells and refactorings. And finally, we introduced the notion of urgency for the microservice security smell instances. This is a bit different. I will describe it during the presentation. And also, we propose the TRIAGE method to systematically triage them. So the figure that you have on the screen illustrate the workflow of the thesis. And from now on, I will go in a little of detail on each of the steps that were done during this whole research. So let's start with the smell and refactoring for microservice security. In this case, we were able to publish this work in the Journal of Systems and Software under the title Smell and Refactoring for Microservice Security, a multivocal literature review. So, as I already told, we applied a multivocal literature review. Why this type of review? Because we were interested in capture the state of art and practice in security microservices. So we started by searching, obviously, the usual way, we applying a string, right, to search in the literature and so on. We ended with 136 candidate studies, and after applying all inclusion and exclusion criteria, we ended with 55 selected primary studies which were analyzed, and then we were able to generate a taxonomy of security smells. So let's start defining, in this case, what is a security smell. We describe security smells as a possible symptom of a bad decision that was taken at a certain point during the design or the implementation of a microservice application, which may impact on the security of this application. The effects of security smells can be mitigated by refactoring the application, while obviously at the same time not changing the functionalities offered to external clients. So this is the description that we propose for microservice security smells, and the way that in which we can mitigate, in this case, the effect that this provoke on the microservice-based application. So, in an effort to scatter the knowledge on security microservices, we concretely wanted to answer the following two research questions. The first is, what are the smells indicating possible security violations in microservice-based applications? And the second one was how to refactor microservice-based applications to mitigate the effects of security smells. The result of this multivocal literature review, and in this case, in a way, in the effort to answer all research questions, we generated this taxonomy that you currently have on the screen. In the left, you have the security properties that are affected by the security smells here in the middle and in orange, in the middle of the figure and in color orange. You have a list of 10 security smells, and then on the right, in green, you have the refactorings that are known to mitigate the effects of these security smells. So let's say an example, just a brief one to give some more context. Let's take, for instance, the centralized authorization security smells, which occurs when a microservice-based application only handles authorization in one component, typically at the edge of the application, while obviously not enacting any fine-grained authorization control or mechanisms at the microservice level. When authorization is managed only at the edge of the application, microservices are exposed to the confused, for example, to the confused deputy problem, since they trust the gateway based on its mere identity, and this can obviously expose the microservices that are forming an applications to misuse if they are internally compromised. So in this case, the affected security property is the authenticity. And in concrete for these smells, we provide a description of the smells, which security properties are affected by these smells, the description of the refactoring that is known to mitigate the effects, and the type of the refactoring, in this case, that is recommended to apply by the practitioners and researchers that obviously wrote the primary studies that we analyzed. So the contribution of this step was a taxonomy that associates 10 security smells with the security properties that can violate and the refactoring that could be applied. An overview of the actual recognitions of each smell in the selected literature in the 55 primary studies, and a discussion of the effects of each security smell and how the corresponding refactorings enable mitigating the risks. Then, in an effort to complement the result that we have obtained by this multivocal literature review, we moved to describe a bit the bad and good security practices that utilizing the same body of knowledge. I will explain this, but this work was, we were able to publish at EXA, in this case, under the title of under the same title of the chapter. So here we have the figure that we saw some minutes ago. This is the structure of the multivocal literature review that we applied. And we started from the same body of knowledge of this, as a result of this multivocal review, the 135 candidate studies. But this time we applied different inclusion and exclusion criteria, resulting in 44 selected primary studies that were then analyzed, and we were able to elicit bad and good security practices in the context of microservice-based application. So for this particular step, we wanted to answer also two research questions. The first one was, what are the known bad practices when securing microservices? And the second one is, what good practices are known to avoid incurring in security issues, the security issues caused by these bad practices? The result of this step was a taxonomy of bad and good practices, as I already had mentioned. On the left, in orange, again, we have the bad practices, in this case, trust the network, no-layer security, and so on. And in the right, in green, we have the good practices that the authors of the selected primary studies recommend in order to avoid incurring in these bad practices. So here we have an example of what the information that we provide. In this case, we have the bad practice called non-layer security. That occurs when designing a microservice-based application by relying only on the perimeter defense and or by implementing a single security solution space. And then the good practice that was, in this case, recommended by the author of the studies to avoid incurring in the problem that could cause this security bad practice is defense in deep. That in this case, this good practice is a strategy in which several layers of security controls are introduced in the application. With this approach, in this case, with this defense in deep good practice, critical microservice can be protected with multiple security layers. This obviously helps slow down attacks when one security mechanism fails, or for example, when a security vulnerability is identified. One of the main advantage of the microservice-based architectures is that specifically this application allows the diversification of security mechanisms, layers, etc. That can be implemented in this type of application. So with regard of the contribution of this step, we have presented a taxonomy including 4 bad security practices and the corresponding good practices that avoid incurring in these problems. And we also provide a discussion of each bad practice by illustrating the security smells, in this case, relating this step to the previous one, signaling and the security issue that it may cause. Okay, so at this point, we have a taxonomy of security smell and refactoring. We have a taxonomy of security bad practices and good practices. Then we moved to we were trying to find a way to identify and resolve, in this case, the security smells that are present could be present in an application. For this objective, with this objective in mind, we collaborated with a model-driven engineering team, and we were able to provide initially a first approach model-driven engineer base for the resolution of microservice security smells. Because of the quality of this proposal, we were awarded with the best student paper at ICSOF in the conference, and we were invited to publish an extension of this work, which was titled Model-Driven Security Smell Resolution in Microservice Architecture using Lemma. I will describe this with a little details now. Then finally, using the knowledge accumulated with these two previous steps, we were able to provide an end-to-end resolution of security smells based obviously in model-driven engineering. So we started relying on the language ecosystem for modeling microservice architectures that is known as Lemma. This language ecosystem was proposed by Florian, that was one of the members of the team that carry out this research in particular. And Lemma provide a set of modeling languages to capture various concerns in microservice-based applications. In this case, Lemma specifically enables the application of model-driven engineer to microservice architecture. In particular, so while relying on Lemma, we were focusing only on three of the language that this approach provide. We were using the technology modeling language, which allows to capture technology decisions related to microservices, their deployments, communication protocols, deployment technologies, and so on. Then the service modeling language allows us to provide, to specify, in this case, microservices, their interface, operation, and endpoints at the service level. Finally, the operation modeling language, in this case, help us supporting the specifications and configuration of microservice containers and infrastructure in general. So as a first step, we extended Lemma, in this case, the approach proposed by Florian, which this step, we were able to model the security aspects of microservices. Then we proposed a method to automatically process these Lemma models, these updated Lemma models, to detect the microservice security smells that are part of our proposed taxonomy. And finally, we are able to recommend the refactorings to resolve their effects, obviously, again, relying on the taxonomy that we have proposed. And we are able to refactor the Lemma model and provide, in this case, to the stakeholders, code generating mechanisms, and I will describe this in a bit. So in order to have an approach to model security smells, we defined a process to model microservice security smells by extending, in this case, the Lemma, the language ecosystem Lemma. We then provide also, or defined a process to detect the microservice security smells in the Lemma model. So we are still at the model level. And finally, we were also able to provide a process, in this case, to refactor these Lemma models in order to resolve the security smell at model level. With this step, we were able to move, in this case, to the end-to-end approach. And we were, at the end, our approach ended with a reconstruction phase, a detection phase, and finally, a resolution phase. Our approach first mapped the source code of an existing microservice-based application to specify, in this case, the architecture models based on LEM. Or the proposed approach in this case is limited to Java-based applications, but in the future we want to try to extend this approach to more languages. These models that are generated taking as a basis the source code of the applications are then validated to automatically detect the security smells and make them visible to the stakeholder of the application. And then we refactor the model to resolve the smell at model level. And finally, we have generated a code, we were able to provide a code generator, just to not repeat myself, which then reflects the changes made at the model level, but now implemented these changes also at code level. For this particular approach, we assess the applicability and effectiveness of our approach by applying it to two microservice-based applications, and we justify, in this case, the usability and effectiveness and applicability through case studies using the Lakeside module application. So, for example, here I'm just showing a figure that contains, in this case, the information that we provide when we detect a security smell at model level. In this case, the lemma model that was generated from the source code of the application. This is the Lemma Eclipse editor, that is a plugin that we can integrate in Eclipse. Then, when we identify the security smell, we provide an interface to the stakeholders to decide, in this case, how to proceed. If they want to refactor the model to mitigate the effects of the security smell, or other two options that, in this case, in particular for the publicly accessible microservice security smell, is ignore this instance of smell. I will explain this later, or to configure the microservice as internal. To be clear, in this case, that a specific microservice will not expose to external clients, so there is no need to expose it through an API gateway. Sorry. Then this is just a figure to showcase, in this case, the refactorings of the model and the change that we are able to implement. So the main contribution of this step was an end-to-end approach for resolving security smells. The approach recovered the software application architectural design using lemma models. So we extract from the source code the lemma model, which contains obviously the information about also security aspect of the Java-based applications to automatically detect the security smells. We also provide, in this case, an interactive mechanism for the resolution of the smell, the figure that we just saw, that we provide some options to the stakeholders. Okay, so at this point, we have the products of the research that we have done until this step. We are able to identify, in this case, the security smells in a microservice application, and to refactor, in this case, the source code of the application, relying on the lemma ecosystem and the refactorings to the models that we are able to make. But Some comments that we were having when we proposed, in this case, the taxonomy of security, smell, and refactoring was, for example, are these security smell specific to microservice-based applications? And my answer always was like, no, we are just capturing the knowledge that was, in this case, wrote by the authors of the primary study that we selected. So this is more or less a proof that these security smells appear in this type of applications. But then we were reasoning about how we can try to relate in a better way this security smell to the microservice-based applications. And we were starting to think about the impacts. So for example, the security smell maybe can appear in other type of applications. Some of them are now part of the OWASP top 10, for example. So how specifically they affect, in this case, the microservice-based applications. To this end, we first starting by proposing a way to illustrate the impact of security smells. So I will move to that now. So we know now at least, right, of 10 security smell that could appear in microservice-based applications, but this smell not only affect the security of the application, but could also affect other quality attributes of an application. And resolving or solving this case, applying a refactoring to a certain security to mitigate the effect of a certain microservice security smell could also impact other properties besides security. In this case, we refactor, right, the security smell uh, to mitigate the effects on security, but we can also spoil, for example, these impacts to other properties. So let's start with an example. In this case, the centralized authorization security smell. When that's it. When a single component is used to centrally authorize external requests sent to a microservice-based application. In this particular case, the security smell can affect, for example, the authenticity of the application, since the request exchange among the microservices are trusted without further authorization controls. This smell can also hurt the decentralization design principle of microservice-based applications, this being a key design principle, since we have a central component managing the authorization of the whole application. This smell can also hurt, for example, the time behavior of the application, because the central authorization component can become a bottleneck if the application considerably grows in the number of microservices. Now, if we apply, in this case, the refactoring that is recommended to mitigate the effect of this smell, we can also, for example, obviously improve in this case, mitigate the impact on security, but applying this refactoring can hurt, for example, the stability of the application, since we will not have fine-grained authorization controls. These authorization controls must be tested independently, which implies then scaling the complexity with respect of the number of microservices. So we have a more complicated testing in this case for our application. This refactoring can also impact, in this case, the resource utilization of a microservice-based applications, since this approach will require, in this case, transmit more information on each request, because we are speaking about fine-grained authorization mechanisms. This information needs to be sent constantly between the services that compose the application. So we then started to think about it, And we found this particular problem that whether to keep a security smell or apply a refactoring to mitigate the effects of security smells is a design decision that deserves careful analysis. Smell and refactorings can impact on several aspects of an application, including other quality attributes besides security and on its adherence to microservice key design principle, as already have discussed. With this in mind, we proposed a method to enact, in this case, the trade-off analysis, relying on software intent dependency graphs. We use, in this case, we exploit the notation of the software's interdependency graphs to illustrate the impacts of these, let's say, two design decisions. That's it's keeping the smell on the application because, for example, it's currently not hurting quality attributes that are really important for the application besides the impact on security. And the construct design decision will be applied the refactoring to mitigate the effects of this particular security smell. So let's take a subset here and a part of the taxonomy that we provide. With this information that we have in the taxonomy and exploiting the notation of the software interdependency graphs, we can then provide this visual panorama of the impact that we have provided here. We are telling that keeping the multiple publicly accessible microservice security smell will impact the confidentiality as we can observe here, and that resolving or mitigating the effects of this particular security smell adding an API gateway can obviously will affect instead, the confidentiality and the authenticity of the application. So we mitigate the impact of the security smell on confidentiality, and we also provide some benefits to the authenticity in the whole application. So let's observe an example. In this case, we started by the security layer in this case, which contains the security properties that we have defined and that are affected by the security smell. We have the two design decisions, in this case, keeping the smell in the system, in the application, or applying a refactoring. We have the impacts of these two design decisions. We then added the layer related to microservice design principles because we were trying to find a way to specifically relate these impacts to microservice-based applications. So what better can rely on the key design principles of this particular architecture. So we have the impacts of this, of keeping the smell and applying a refactoring on the key design principles. And then we added two other dimensions, in this case, performance efficiency and maintainability. So we can, with this approach, obviously we can have a visual and holistic panorama of the impacts of the security smell and the refactoring that is known to mitigate its effects. So we had a four-dimensional analysis. In this case, is recommended by the literature relate to trade-off and so on, to keep at maximum a four-dimensional analysis, because then start becoming really or scaling in complexity. Sorry. So the principal, the main contribution of this step was a method that used software interdependency graphs, in this case, relies right on the notation, to provide a visual analytic panorama of the positive and negative impacts of each security smell and refactoring. This method provides support for analyzing the possible trade-off related to keeping a security smell in the application or applying a refactoring. So until this step, we have now a method to also illustrate the impact of security smells, but we were interested on validating these impacts with practitioners and researchers that work with this type of applications. Because we have, in this case, a method to showcase, to illustrate the impacts, but these are impacts, sorry, I will correct myself, but we wanted the following step, identify concretely which impacts are known when we incur in these to design decisions. So we started by publishing, in this case, the result of a survey that I will describe now, under the title To Security and Beyond on the impacts of microservice security smells. Then for the quality of this work, we were invited to send an extension of this work, which title is Beyond Security, Understanding the Multiple Impacts of Security Smell for Microservices. I will describe now what we were focused on this step. So as I already explained, we were trying to answer this specific question. Are the security smells and refactorings impacting on maintainability, performance efficiency, and adherence to microservice key design principles? As a research question for this step, we wanted also to provide information about the level of agreement of the practitioners and researchers that have participated in this survey, and if there was any discrepancy between practitioner and research. We were interested also in knowing a bit of context of this. So in the screen, we have a figure that describes the process. Again, we start again utilizing the information recovered in the multivocal literature review, relying on the 55 selected preliminary studies. Then analyzing these studies, we were able to identify 42 possible impacts related to security smells and the refactorings. Then with the online survey, in which practitioners and researchers have participated, we were able to validate 35 of these specific impacts. So let's describe a bit about the survey that we did. So the survey was structured with initial profiling question to know more about the respondents. In this case, right, we were interested to know if there was any difference between practitioners and academics that work with this type of application. So that's the reason behind these questions. Then the participants were exposed to the 42 statements that we found in the primary studies. And here is a bit of the information about the participant. In this case, we wanted with 13 industrial practitioners. In this case, 8 of them were software architects, and 9 academic researchers participated during the survey. So, as I already have explained, but sorry for repeating myself, but I want this to make really clear. We wanted to answer what are the impacts of each of the smells that are part of our taxonomy. In this example, we have again the centralized authorization that was used to exemplify, right, the method that we provide to illustrate all the impacts. So we wanted to know common maintainability, performance efficiency, and microservice key design principles are affected. So the survey exposed the participants to the 42 statements that are related to the security smell and refactorings. Here on the right, we have the statement, in this case, for the centralized authorization, security smell, and the refactoring also. We can, for example, here is one related to the smell, and here is one related to the refactoring. So then we measure, in this case, the level of agreement of the respondents with regard to the statement that they were exposed. And on the left, you have, in this case, how we show it, in this case, the level of agreement of the practitioner and researchers that have participated during the survey. We only considered those impacts that reach more than 50% of agreements. So in the case of the centralized authorization security smell, we discarded two impacts because the level of agreement uh, was not high enough. We also were, as I already have mentioned, right, we're also interested in knowing if there are any discrepancy between practitioner and researchers. We didn't find like any weird stuff. We just showed this information. In some scenarios, there was some discrepancy. I will describe a bit of this now, but in general, they were really aligned in this case with the agreement on the statements related to the impacts of security smell and refractory. So with that information, we were able in this case to color or to draw in this case the arrows on the proposed approach to illustrate the impacts of the two design decision, right? The keeping the security smell on applying a refractor in the proposed four-dimensional analysis. So the contribution of this step was 35 confirmed impacts, a discussion in this case of the answer given by practitioners. And obviously, we were able with this information to generate all the six that illustrate in this case the impacts of each of the security smells and refactoring that are part of the proposed taxonomy. Perfect. Now we move to the final step of this research that is called triaging microservice security smell with trees. I will explain now this. We are happy to announce in this case that this work was accepted after obviously the commission knowing about this presentation. We got the news that the work was accepted in the conference. So let's start by with this example. In this case, we have an architecture of the lakeside mutual application. When working with microservice security smells, we found that these smells can affect the service that compose an application in different ways. So we started now defining security smell instances. That is a security smell affecting a particular service. In this case, it will be seen as a pair smell service. So in this particular application, we were able to find 32 different instances of the security smells. In this case, 5 of the security smells that are part of the proposed taxonomy. So with this in mind, we move to the following problem. So now at this step, we know that multiple security smell instances can affect multiple services in a microservice-based application. So architects must not only find the trade-off for each smell instance, but also decide which smell instances resolve fear. Some smell instances may be more urgent than others because they affect services that implement core functionalities and or quality attributes that are critical for a specific service, for example. So we wanted to answer questions as how does each security smell instance impact on a microservice-based application quality? And more generally, we wanted to answer which security smell instances are more urgent to others. With this in mind, we propose the trees method that relies on the service relevance, on the importance of the quality attributes for this particular service, on the impacts that we validated, right, with practitioners and researchers of the security smell and refactories on the quality attributes. Then with trees, we are able to provide an urgency code for each of the security smell instances that are currently affecting an application. So this is the triage matrix that we use during the trees method. This matrix enable assigning each security smell instance with an urgency code varying from highly urgent to non-urgent. So we cluster in this case the smell instances affecting an application in urgency classes that you can observe here in the diagonals that are part of the matrix. So with this method, we are able to triage, in this case, the smell instances that are currently affecting an application. And to validate this proposed method, we did an experiment with 26 practitioners. The experiment consisted of asking practitioners to triage a subset of the microservice security spell instances affecting the lakeside mutual application. That's it, a subset of the 32 security spell instances that we found in this particular application. And the research question associated with this validation is where history is easing the triage of microservice security smells, and history is increasing the confidence of practitioners in the results of the triage process. Here in the screen, we have some figures that illustrate the distribution of the urgency codes assigned by practitioners. The light blue boxes represent the urgency codes assigned without the TRIS method, and the dark blue represent the urgency codes assigned using the TRIS method. We found that while there was some straightforward case, in this case illustrated by this box, I will not stop explaining this in detail about the tasks that were to where the participants of the experiment were exposed. But this, in concrete, is a straightforward case where a security smell was impacting a critical quality attribute but for a highly relevant service. So in this case, the triage was straightforward, using or not the method, but we found that the method is really useful in the more complicated cases, as we can see, observed, for example, in this particular box plot. The top box plot represents the urgency code assigned by the experienced practitioners that participated in the experiment. And the box in the bottom represents the urgency code assigned by the unexperienced practitioners that participate on the experiment. So with regards of the research question, is it easy the triage of microservice security spells? We found that yes, that most of the subjects that had participated in the experiment found that the given triage tasks were moderately complex or complex when working without trees, as shown by the light blue bars. While when using the triage method that we have proposed, they found the exact same task easy or very easy. With regards of the confidence of the practitioners in the results that they obtained with the triage process, they were generally more confident, as shown by the figure, in the results that they obtained with the triage method that we have proposed. Also, when using the triage method, most of the experienced practitioners, as we can observe in this figure, reduce their self-confidence on the, let's call them, intuitive triage assignments. And in the case of the urgency codes that were assigned without the TRIS method, 47.6% of them were revised when using the triage method. In this case, were revised downwards. That means that the general urgency of those particular security smells have decreased after utilizing the triage method. So with regards to the contribution of this step, we have proposed a triage method to systematically assign urgency codes to the microservice security smell instances that can appear in a microservice-based application. So that's the final step of this whole research. Now I will quickly move, sorry for the time, but I will quickly move to the conclusion and future work just to close the presentation. So this thesis has report on what is being said by practitioners and researchers about known security problems in the context of microservice-based application. During this thesis, we have also been able to provide an end-to-end approach, an end-to-end model-driven approach for resolving the security smell that can appear in a microservice-based application. We also have introduced a method to enact the trade-off analysis of microservice security smell and refactoring using solvable interdependency graphs. That is illustrating, right, the impacts that these different design decisions have. And finally, borrowing from hospital emergency rooms triage practices, in this thesis, we have introduced the notion of urgency for microservice security smells, and we have proposed the TRIAGE method in this case to systematically triage them. In the case of future work of the microservice security smell and bad and good practices, security is always evolving. So I think that an important line of research is keep obviously doing a step in order to address the challenge, the security challenge that currently part of this particular architecture. So we can extend, for example, the taxonomy that we have proposed. In the case of the model-driven end-to-end resolution approach that we have proposed, as I already have mentioned in this particular step, we focus only on Java-based applications. So a way to extend or a new, for example, line of research could be focus on other programming languages to, in this case, support the resolution of security smells in different, in other applications. With regards of the visual and holistic panorama, that is the four-dimensional analysis, I would really like a way to have or to change or to play, let's say that like this, to play with the four dimensions that we have proposed. For example, change maintainability with another quality attribute. In this case, will take a further research will take get or to collect information about the specific impacts of security smell and refactoring on different quality attributes, beside in this case security, maintainability, performance efficiency, and microservice key design principles. So that will be a way also to extend in this case the research done in the context of the impacts of security smell and refactoring. And finally, TRIAGE, in this case, a new line of research. We are currently, I think I can mention this, but we are we are happy to announce that we are using currently the output of TRIAGE as an input of another method that we have recently proposed in EXA, and we were accepted recently also. So you will have news from us soon, I expect. So this is the list of publications that were the result of this whole research. In this case, we count with 11 publications. Two of them are currently waiting for publication. In this case, to the Clay Journal was submitted. We already got the first round of review, and we are happy about them. So we hope we can publish this soon. And in this case, we were accepted recently with the work done in the context of triaging microservice security smells. So sorry for taking that long. It was a long process. So I hope you somehow enjoyed this journey